I usually wait for a ding. I didn't know if I started or not. I have. Hey there, algebra. We are in Unit 4, Lesson 6, Features of Graphs. So we've been talking about functions the past 5 lessons, and here we have features of graphs. So let's warm up a little bit. Draw. It's been a little while since I recorded a lesson. So Diego is walking home from school at a constant rate. This graph represents function d, which gives his distance from home in kilometers, m minutes since leaving the school. So this function, I would write d is a function of minutes, okay? And that's going to be distance from home, m minutes since leaving school. So he's going to get closer to home as time goes on. Okay, so use this graph to find or estimate d at 0. That means our input is 0, and we're going to look on our graph when the input, or x, is 0. It seems to be approximately 2.25 meters close to home, right? And we look at d evaluated at 12. Here's 12. Again, I can't read that one extremely accurately, but it looks to be, I don't know, maybe 0.9 meters. I had a phone call. I'm not sure where I left off, so we're going to start again. I have the solution to d of m is 1. That means our output is 1, and this side right here is our output side. Okay, so what I really need to do, let's just go ahead and change colors, and we're going to talk about our output. So when 1 is our output, what is our input? So I'm going to follow this, hit the graph, and then go straight down. So the input looks to be about 11 minutes. Okay, approximately. So we know the output, we follow it back to the graph, and then go down to the x-axis to find the input. And how about the solution to the graph? The solution to d of m equals 0. So sorry. So there we know the output is 0. We need to go and trace this to the graph and find the input. So at minute 20, our distance from home is 0. That means it took him 20 minutes to get home from school. Number 3 means at minute 11, the distance from home is 1 kilometer. Okay, that's that. Let's move on. All right, a toy rocket and a drone. Okay, let's go back to a less eye-hurting color. Here we have a toy rocket and a drone. They were launched at the same time. So we see here time is our input. They're launched at the exact same time. Here are the graphs that represent the heights of the two objects as a function of time since they were launched. Height is measured in meters above the ground, and time is measured in seconds since launch. So this is our input. It's our independent variable, and this is our output. It's our dependent variable. Analyze the graphs and describe as precisely as you can what was happening with each object. Your description should be complete and precise enough that somebody who is not looking at the graph could visualize how the objects were behaving. So I'm going to look at the graph and describe one object at a time. So if I look at the drone, it took off from the ground at time equals 0 seconds. It slowly, I'm trying to use all the words, slowly rose, steadily. We want to make sure that we know that it's a steady rise Oh, not steadily. Steadily? I don't know how to spell that. I think that's right. It rose steadily. Let's say this. It rose at a steady rate until reaching the max height at 2 seconds. I'm running out of room. It hovered. I like that word. It's like English meets math. It hovered. Ooh, I didn't say what the max height was. Reaching the max height of 20 meters. That's important. It hovered or stayed at 20 meters until, oh my word, until time equals 5 seconds? Yeah. So it stayed at 20 meters until time equals 5 seconds. And then it slowly fell, decreased in height, at a steady rate my handwriting until time equaled 7 seconds. That's a lot of words, isn't it? Okay, go ahead and push pause and write that down. And then I'm going to talk about the rocket, okay? So I'm going to ask you to push pause because I'm going to erase this. And I think I can lasso select it. That's not the lasso. Bummer, it didn't work. I'm going to try one more time because it will be easier. I think if I just hit the delete button. It worked. All right, now let's talk about the rocket. So the rocket, we can see that at time equals 0, it starts 25 meters above the ground. The rocket was launched at time equals 0, 25 meters above the ground. At time equals about 2 seconds, the rocket reached its maximum height of about 45 meters before falling back to the ground the rocket, I'm making this up as I go along, so there's no prescribed words here. The rocket reached the ground at what time? 5 seconds. Okay, so I analyzed the graphs. I described as precisely as I could what was happening with each object. My description should be complete and precise enough that somebody who is not looking at the graph could visualize how the objects were behaving. So basically that means somebody, oh, the 5 seconds is moving along with me, that's funny. Somebody could read this description and make their own graph, and it would be very accurate. Okay, that's the goal here. It's very dark over here. All right, see what I can do with that seconds. Sometimes this happens. I don't know why. And now it's 5 seconds drawn in black ink. All right, so we're not looking at this activity synthesis yet, so ignore that. Which parts or features of the graphs show important information about each object's movement? List the features or mark them on the graphs. So let's see, what are the things that we want to do? I know the height the rocket is launched from is very important, okay? Okay, I'm going to push pause and copy that onto another page so I can look at it fresh, okay? Hold on a second. Okay, there are quite a few very important parts about this graph. Really, when time equals 0, what's going on? Which would be at each graph, like what's going on at time equals 0. Okay, very important parts. And then we can say, let's say when the graph reaches or crosses the horizontal axis, very important, okay? So that point, and that point. They're very important parts, okay? Let's change colors again. The points when the graph changes direction, which right here for this one, we went from going up to going down, or right here and right there, we went from going up to staying steady, not moving, no change, to going down, very important. The shape of each curve, which I didn't do a good job, so I'll put that in red. The shape of the curves, straight lines, which I said steady, but I should have used better descriptors. Straight lines or curves, right? I'm out of colors. Ooh, I've not tried to do this. Let's do purple. Intervals when graphs behave a certain way, that means here it's not changing. Here we're straight line down, straight line up, things like that. Intervals when the graphs behave a certain way. And that's really it. So those are the things that we want to pay attention to. What's going on when time equals 0, when the graph reaches or crosses the horizontal axis, changes direction, the shape of the curves, and the intervals. Okay, those are all very important things. Let's go back up to where we were. All right, so we did that at the end, right? All right, well, let's see, what are we doing here? Yep, we're good. Okay, so now we're going to talk about bungee jumping. In a bungee jump, the height of the jumper is a function of time since the jump begins. The function h defines the height in meters of the jumper above a river, t seconds since leaving the platform. So h of t is our function. Here's a function h followed by 5 expressions or equations and 5 graphical features. So here are 5 expressions or equations and graphical features. I'm going to remind you guys, an expression is something like this one right here, where it's just h of 0. An equation has an equal sign in it. H of t equals 0. Expression, equation, equation, descriptions, okay, graphical features. So let's go ahead and match each description about the jump to a corresponding expression or equation and to a feature on the graph. So we have 3 things to match up, right? Do I have a table here? One expression or equation does not have a matching verbal description. Its corresponding graphical feature also is not shown on the graph. Interpret that expression or equation in terms of the jump and in terms of the graph of the function. Record your interpretation in the last row of the table. All right, so we have a graph, h of 0, that would be the height at time equals 0. So the greatest height the jumper is from the river, the height from which the jumper was jumping. So it's not necessarily greatest, because remember the jumper goes down and then bounces up higher and then goes down. Okay, so that would be h of 0. And that would also be the vertical intercept. So that right there is h of 0 and the vertical intercept. So we used h of 0 and vertical intercept. All right. The greatest height the jumper is from the river. It looks like we're looking for the highest number, okay? So h of t equals 80, h of t equals 45. If I look right here, ooh, I did not read that well. That's also that point right there. So that's also h of t equals 80. Those are the same. I got distracted again. So let's see what happens. So we have maximum and h of t equals 80. So all of those things for that maximum, for that point right there, like 4 different things for that point on the graph. So let's fill that in here. Greatest height, h of t equals 80. And the feature on the graph is still, it's our maximum. This would be the vertical intercept. For this particular graph, those are the same things, and that's okay. Okay, the maximum and the vertical intercept. The time at which the jumper reaches the highest point after the first bounce. So let's look at it. So jumps, bounces up, right there. So that would be less than 10. And it looks to be about 45. So that's h of t equals 45. And that would be our first peak in the graph. The lowest point the jumper reached in the entire jump. That would be right here. And I would say that would be h of 4. And that is the lowest peak, first dip in the graph. Cool. Now, we did not use h of t equals 0 in the horizontal intercept. Let's talk about that. I'm going to go ahead and change colors. Okay, this is my horizontal axis. Does this graph cross the x-axis anywhere? So h of t equals 0, that means if I were following, I'd follow my graph over here, wait until it crosses my curve somewhere, and then go down and read the time. But it doesn't. Like h of t equals 10, t equals 4. H of t equals 45, t equals, I don't know, about 8. Okay, but h of t equals 0 does not exist. Our horizontal intercept, there isn't one. What would that mean if there actually were one? Okay, oh goodness. How did I fix this last time? Hold on. So here for part E, it would be time. We talked about the horizontal axis, the horizontal intercept. What would that mean? The time at which the jumper reaches the water. And that shouldn't happen. Okay, that shouldn't happen. The jumper should not reach the water in a bungee jump, or somebody calculated something wrong. So that is just h of t equals 0 and your horizontal intercept. Not a good thing. All right, now use the graph to estimate h of 0, time equals 0, and h of 4. We already did h of 0. So at time equals 0, it's at its maximum, it's 80. And then h of 4, that's at time equals 4, and I believe we're at our minimum. Yep, we're at 10. So at 4 seconds, right? At 4 seconds, we are 10 meters above the river, and at 0 seconds, we're 80 meters above the river. And then estimate the solutions to h of t equals 45. So when my output is 45, let's change colors. When my output is 45, my input is, that's not 45, sorry. When my output is 45, my input is about 8. And then the other question is h of t equals 0. Okay, that would be you've hit the river, and that's not going to happen. Actually, sorry, I just realized h of t equals 45. It's going to happen just right there. Oh, it also happens, oh golly. It also happened right there. So sorry. So we do hit 45 meters above the water at about 2 seconds, and then again at about 8 seconds, or 9, I don't know. It's a guesstimate, but it does go through that 45-degree mark twice. And this would be no solution because the jumper does not reach the water. Okay, it just doesn't happen. All right, that's good. And that's what we did earlier. Okay, this was longer than I expected, so I'm sorry, but you have plenty of time to work on your problem set. Good job.